this chapter of Year 2 Mechanics, we're going to be looking at moments. Now, moments is essentially a turning force. It's the simplest way to imagine it. So when I say a turning force, I mean not just a force like a push, but a force which is causing the object to turn or to rotate. So here I've got a simple example of a spanner, and then I've got a force on it this way. So obviously I'm going to turn this bolt and screw it in like this, so turning it clockwise. Okay. So in this example here, the way that we calculate a moment is to do the force times the distance. Okay. So a bigger moment or a bigger turning force will be caused by either a bigger force or a bigger distance. So for example, if I made this spanner much longer, you wouldn't need quite as much force to apply to it to turn it. And hopefully that's something that you've experienced in real life. Maybe if you're using like an Allen key, one of these kind of L-shaped things to screw together some IKEA furniture, you know that if you use it this way with your hand here, that's much easier to turn the screw in than it is if you do it this way. Okay, and the reason is that this distance here is then much longer, so you have a much greater moment for the same force. So in this example here, the moment here would simply be 12 newtons times 0.2 meters. So what's that? 2.4. And then the units, you can see the units here, newtons times meters. So we could either write Newton meters. That's probably the simplest unit to use for turning force. Okay. Now, to make this definition slightly clearer, we should technically use moment is the perpendicular force times the distance, or the force times the perpendicular distance, but we'll come on to that in a moment. What I want you to do first of all, I've got an interactive kind of simulation, or basically a game, that I'm going to send you a link to as well underneath this video. And this is quite good just to practice getting the concept of moments and what they are. So remember, it's force times distance. So here I've got to try and balance this weight. So I've got 5 kilograms. As you can put the distances on, but we'll just do it with numbers. So we've got obviously a mass of 5, which is distance 1 away on one side of the pivot. Well, to balance that, I obviously need 5, which is 1 away. Okay, that one's quite simple. But they get harder and harder and more complicated. So if we look at some of the ones in level 2. So here it says what will happen. So here we've got 10 kilograms distance 2 away. So that would be a moment of 20. And over here, we've got 10 distance of 3 away, so that would be a moment of 30. Now, in terms of the actual moment, it wouldn't quite be 30 because actually we'd have to do 10g times the distance. So in terms of real life, we'd have to do 10g for the force times the distance of 0.5. So this would actually be 10 times 9.8 and then times 0.5. This would be 10 times 9.8 times 0.75. But to make the numbers easier, we can just use these. So the bigger moment is clearly on this side because the distance is larger. So it's going to do this. So this is quite a nice interactive activity to have a play with, just to make sure that you understand the concepts. So here, the pivots here, we've got a mass of 20, which is 2 away, so that's a moment of 40. And here we've got 40, so if we put that just the distance of 1 away, then that should balance. Okay. So I suggest you spend a few minutes just having a play with that, and you can try the different kind of difficulty levels and things. They're quite fun. Okay. So coming back onto this slightly more complicated definition. So if we've got a force at an angle, so in the first example it was easy because it was perpendicular, so that was easy. But really our stricter definition is either the perpendicular component of the force times the distance, or the force times the perpendicular distance. Now here I've got exactly the same example, but I've just drawn the diagram slightly differently. So I've got a spanner of length 0.2 or 20 centimeters. And then I've got a force of 12 newtons at an angle of 30 degrees to the spanner. So if I use this first definition here, the perpendicular component of the force, so I want to resolve this 12 newtons into this red component here, because this is the component that is perpendicular to this line here. We call this the line of action of the force. Okay, so it's perpendicular to the distance. So we've got the line of action here, and they've got the distance here, and they're perpendicular. So we want this component here. So this would be 12 Now if this is 30, you could say that maybe this is 60, or if I drew that triangle there in, that angle up there is 30, because this is a right angle. So you've got 12 sine 30. Okay, you could also draw it there. That would be the same force. So you've got 12 sine 30 is the perpendicular component of the force times the distance of 0.2. So you've got 12 times sine 30 times 0.2. So you get 1.2 Newton meters. And we should also state its direction. Here, because the force is this way, this is making it rotate like that. So that is clockwise. Okay. You could also do 12 cos 60, which would obviously give you the same value. Now this interpretation over here, instead, this one we're going to split up using the second definition, and we'll show that we get the same result. So the moment is the force times the perpendicular distance to the line of action of the force. So it's still exactly the same situation, but this time I'm going to leave my force as it is. So I'm going to say at the moment is 12 times, now I'm going to resolve the distance instead. So I've got to resolve the distance so that it's perpendicular. So I want this red component here, because this 0.2 is the hypotenuse. This side here, you can see it's opposite the 30, so that's going to be 0.2 sine 30. And we still get 1.2 Newton meters clockwise. Okay, so you can either resolve the force and split that up so that they're perpendicular, or you can resolve the distance so that the force and the distance are perpendicular. As long as you do either, you can see in the calculation you've got 12, you've got sine 30, and you've got 0.2. They are exactly equivalent. Some situations lend themselves better to this interpretation. Some situations lend themselves more to this one. When I'm doing problems, I normally resolve the force if I can, just because that's what we do in other bits of mechanics. But sometimes just the way the diagram looks, it actually ends up easier to do this. Just kind of depends on the diagram and which triangles you can spot easiest, really. Okay, so a couple of examples just to calculate. So find the moment of each force about the point P. So here this point P is fixed, and then we are applying a force here. So this is going to move, maybe this is like a rod. Maybe imagine this is like a metal rod here, this 3 meters, and we're going to make it rotate anti-clockwise. Okay, so that's what this 6 is doing. It's forcing it to go like that. Okay. So here, they're already perpendicular. So I don't need to do any clever resolving here. They're already perpendicular. So the moment, the way that we would write this is the moment about P, like that. M about P is simply 3 times 6, so that's 18 Newton meters anti-clockwise. Now here, in case B, so again, we've got this fixed point P, and perhaps this is like a metal rod here, and we're applying a force of 12 newtons this way, so that's going to make it rotate like that. Okay, so this is obviously going to come out as being clockwise. Now here we need to resolve it. We can either resolve the force or the distance. I'm going to split the distance up here because you can see from the diagram they've already drawn this dashed line in. So if this is 8 meters and this is 35, this distance is 8 sine 35 meters. So I can just say that the moment about P here is force times the perpendicular distance of 8 sine 35. And that is 55 Newton meters. And that is moving clockwise. Okay. Okay, so in this one it says a diagram shows two forces acting on a lamina. When we say a lamina, it says this down here actually, a lamina is a 2D object whose thickness can be ignored. So I would imagine like a piece of paper, okay, just like a flat object essentially. Find the moment of each of the forces about the point P. Okay, so again, this point here, P is fixed, and we've got a force here which is trying to get P to rotate this way, so that is clockwise. So we've got 5 times 2, they are already perpendicular, so that's 10 Newton meters clockwise. And now we've got this other force here, the 8, which is at an angle. Again, I'm going to resolve the distance, I think, to make them perpendicular, like that. So this distance here is then 2 sine 50 for the perpendicular distance. So we've got 2 sine 50 times 8 newtons. Let's work out what that is. So that's 12.3 Newton meters, and that force is trying to make it rotate around that way. So that is anti-clockwise. So overall, we can work out what's going to happen. We've got a force of 10 Newton meters clockwise, and we've got a force of 12.3 Newton meters anti-clockwise. So overall, we could find the net moment, or the resultant moment, is obviously going to be 2.3 Newton meters for the difference between them, and it's going to go anti-clockwise overall. So overall, this will rotate that way. Okay. Okay, so you can have a go at 4a if you want to, but I'd actually recommend just listening to the next few examples and then doing 4b instead. Okay, but you can have a look at those if you want to. Okay. So here we've got a set of forces acting on a rod. Calculate the resultant moment about the point P. Okay, so you've got this pivot here, point P, and then we've got these different forces that are all different distances away. So we've just got to analyse each one. So the 5 newtons here, if this is my pivot and this is upwards, this is going to make it rotate clockwise. Okay, so I've got 5 newtons times a distance of, well, it's 3 meters away. So that's 15 Newton meters clockwise. I've got the 4 newtons here, which is a distance of 1 meter away. And these are all perpendicular, so this makes this quite easy. So that's obviously 4 Newton meters. But the 4, that's forcing it to rotate this way, right? So that is anti-clockwise. And then lastly, I've got the 3 newtons, which again is a distance 1 meter away. So that's 3 Newton meters. Now this one, let's do this in a different color. If this is the pivot and it's here, that's forcing it to turn this way. Okay, like that. So that is also anti-clockwise. Okay. So in total, we've got 15 clockwise, and then we've got 7 anti-clockwise. So we've got 15 clockwise, 7 anti-clockwise. So obviously that is then at 8 Newton meters clockwise is what will happen overall. That'd be the resultant moment. Okay, this one, similar idea, but we've got some angles instead this time. So here's our pivot, point P. Okay, so let's deal with the 5 newtons first of all. So this is trying to make it rotate clockwise. Okay, if I put it in that direction, it's going to go around like this. So this is a clockwise moment. We've got, need to resolve it. So I'm going to do the distance, so that is 4 meters away, times the perpendicular force. So I'm going to split this force up here. Okay. Now I know that when I split it up like that, it looks like the distance is shorter, but it's not. The distance is, the force is still applied at this point here. If it helps, you could maybe resolve it. Instead of there, you could draw it like that. That would be the same thing. Okay. But that force there is going to be 5 sine 80. And that's a force, that's in newtons. So you've got 4 times 5 sine 80. So that's 19.7 newtons, and that is making it go clockwise. Now we've got the 6 newtons here. This is obviously going to make it go anti-clockwise. So that is 6 newtons times the distance is already perpendicular of 3. So that's 18 Newton meters anti-clockwise. And then lastly, we've got this 4 newtons. Now this is on the right hand side of the pivot, and it's pulling it that way, so this is going to make it go this way. So that is anti-clockwise. So I've got a distance of 3 meters. Now I'm going to resolve the force again. So I can split it by this, But again, it does kind of make it look a bit confusing maybe, so you might want to split it up there instead. And that's going to be 4 sine 40. If you drew it here, you could say that this here is 50, and you could do 4 cos 50. And 4 cos 50 is exactly the same as 4 sine 40, so it doesn't matter which you do. So I'm going to do times 4 sine 40. So that's 12 sine 40, which gives me 7.7. And that is going this way, so that's anti-clockwise. Okay. So we've got a total clockwise moment of 19.7, total anti-clockwise of 18 plus 7.7, so that's 25.7. So overall, 25.7 minus 19.7, so we've got 6 Newton meters anti-clockwise would be our resultant moment here. So overall, this point is going to rotate anti-clockwise, so in this direction, with 6 Newton meters of turning force. Okay, so again, we've got another laminar, and it's rotating about this point P. So we've got a force of 7 newtons, which is a distance of 8 away, and we've got a force of 4 newtons, which is also a distance of 8 away, and they're obviously at different angles. Now what I might do here is actually resolve the forces like this to make it more obvious, because they act at this point here. So maybe that makes it a bit more obvious. Okay. So if that's 25, and this angle in here is 90 minus 25, which is 65. So this component here, you could either have it as 7 cos 65. This angle up here would still be 25, or you could have 7 sine 25. Okay, they are the same thing. Because now we've got this right angle in here, so the force, or the component of the force, is perpendicular to the distance. So we've got 7 sine 25 times the distance of 8. So that is 23.7. And that is trying to make it rotate. It's a bit clearer now that I've got this arrow on here. This is trying to make it rotate clockwise. Let's do it in a different color. We've also got this force here. So if I'm looking for this component here, so we get a right angle in here between the distance and the force. So if this is 35, we could say that this angle here is 35. It's like a Z angle. So this is then 4 sine 35. Okay. Or this angle here, the little curved bit in there, is 90 minus 35, which is 55. So then that would be 4 cos 55. Okay, both of these values are the same. So I've got 4 sine 35 times distance of 8, which gives me 18.4 Newton meters, and that is going anti-clockwise. So in total, we are going clockwise with 23.7 minus 18.4. So that's 5.3 Newton meters clockwise. So the important thing here is just forming a 90-degree angle between your force component and the distance, or you might split up the distance instead, like on some of the previous examples that we did. There's one where we split up the distance, like this one here. Here we split the distance so that then that was perpendicular to the force. That's the key thing. Okay. Cool. So you should now be able to have a go at exercise 4b, which is all about finding resultant moments.